All right. Well, thank you, everyone. Thank you, Sergey, for the invitation, and thank you, everyone, for coming to this talk. Большое спасибо. And we're going to be talking today about a feature that's actually new in C++20. It was just voted in the past year, and it builds on work that was done before C++20, actually for C++17, trying to solve a problem in C++ code to make it simpler, more efficient, have fewer pitfalls, but still be true to the spirit of C++. And one of the reasons that the proposals before C++20 fell short and did not get consensus was because trying to do it late in the C++17 cycle, there were constraints on what we could do. And in particular, adding a whole new operator to the language seemed to be more than we could consider. But now that we have a brand new standard in front of us, we were able to do it right. And so I'm very pleased with the result. And although this proposal is one that I wrote, it builds on other people's proposals. There have been quite a few in this area. So let me start with a motivating example first. And this is to sort of set the goal as to what we're trying to achieve. So as perhaps you've done yourself, perhaps you've written a case-insensitive string class. Many of us have done that. Well, once we have a case-insensitive string, CIString, we want to compare those objects. We want to compare them with each other, so two CI strings, and we might want to compare them with C-style strings, which are a const char star. And if we want to do that, how many functions do we need to write without using this new feature in existing C++17? Well, even if we ignore const expr and no except and those kinds of things, the answer is quite a few. So the first set of functions is the homogeneous comparison between two CI strings. And there we make it a friend bool. Notice it's not a member, it's a non-member, and a friend, which we just declare and define inline for convenience. But it has to be a non-member so that we get conversions on both sides. If you compare something that can be converted to a string, a CI string, well, we want that conversion to happen on both parameters, so we make it a non-member. And so we have 6 of those comparison functions because we want to support all 6 comparisons. But then we also want to compare the CI string with a const char star, and we want that comparison to be symmetric. We want to be able to put the const char star on either side so that if we compare A less than B, we can also compare B less than A, for example. And so we need 2 sets of 6 functions for that. And this is assuming that there is no implicit conversion from const char star to CI string. Normally we try to avoid implicit conversions. And so we need to write these 18 functions in C++17. And we can already see there's a problem here if we have to write more functions than the number of the standard. Well, we don't want to write this much code, and so much of it, as we can see, is repetitive. In C++20, we can write exactly 2 functions instead of those 18. And I'll go into detail as to what these are, but you'll notice that they are a new comparison operator, which you might have seen already in other languages. It's the 3-way comparison operator that's often commonly called the spaceship operator because it looks like a UFO, or if you're a Star Wars fan, it looks like a TIE fighter. So let's see more about how this can make us, instead of writing all this code, write just these 2 lines of code, and why these 2 lines are actually more powerful and have fewer pitfalls and are strictly more efficient than those 18 lines we had to write before. There's a hint here, because if you look at the return type of the previous functions was bool. Is A less than B? Well, the answer is a bool, true or false. But now here we have a 3-way result, but instead of it just being an integer, say -1, 0, or +1, like strcomp would do, we actually have a type. Now we can leverage C++'s strong typing, and because we said weak ordering is the return type, that means that we get all the 6 2-way operators generated. We have an efficient single pass implementation because all of the 2-way operators simply delegate directly to this 3-way operator, and I'll show why that's more efficient in some cases. We get symmetry on both sides, and it documents with that return type that we're not just returning any ordering, we're returning a weak ordering, which is distinct from, say, a strong total ordering, even though it supports exactly the same functions. So we're carrying more information because we're using the type system. So here's the overview of this feature and how it's designed. We wanted to have, if we're going to address this area of comparisons, we wanted to have a solution that was complete, that addressed all the 6 existing comparisons, plus we knew that C++ was missing a three-way comparison. We wanted to make sure that it could handle all the kinds of comparisons that we could do, including a partial ordering, which is typically difficult to represent because it's not as mathematically intuitive to, even though it's mathematically well-defined and sound, is not as intuitive to a lot of programmers, and it has, let's just say, some difficult bits. We also wanted to deal with symmetry so that just by default, if I can do A less than B, I can also do B less than A. And heterogeneity. So for the same reason, if I do A less than B, even if those are of different types, I should be able to do B less than A. So that's the completeness. The correctness, we had a lot of discussions in the committee about how we should make the default semantics for comparison. And there were many proposals for this, many heuristics or rules of thumb to use. And my paper just said, look, what we need to do, and some other papers said this as well, we just need to follow assignment and copying. If you copy A equals B, so that now with normal semantics, A is a copy of B, it should just follow that you then compare them, you should immediately get A equality B, A equal B, be true. And that means that we should, for instance, generate the comparison under the same conditions that we generate equality. And certainly if we have default, if we know that we're getting default copying, then we should be able to get default comparison for free. And so you're going to see that with equals default. We want it to be efficient, always single pass, to avoid the problem that you actually saw if you looked carefully on the first example today, where we write them today and we delegate one function in terms of the others. So often we'll write less than or equal to in terms of less than or equal to, which can require 2 computations. You might have to scan the equal prefix twice. Well, we don't want to avoid that kind of overhead and have it always be efficient single pass. And we want it to be simple and teachable so that we get to write less ceremony and less boilerplate code. So here in one slide is what we teach programmers for C++20. And you'll notice that you can pick your spaceship of choice. So if you prefer the good guys, then the Millennium Falcon is your spaceship, even though, yes, it kind of looks like a TIE fighter. So we teach that the three-way comparison operator, less equal greater, is what you write to enable comparisons of your type X with objects of type Y. All you do is you write auto, so notice the return type is deduced, X, operator spaceship, const X reference, const. Now, you get to write auto to deduce if you write equals default for your body. It's especially convenient if you write equals default. And equals default as your implementation by default goes through and does a member-wise comparison. So if you have 2 strings as members of your class, we will compare first one, then the other. That will be the default lexicographical ordering in the order that those are declared in your class. And this way, if you write just this one function, we will, depending on the return type that you write, which is something you can write explicitly, I'll show on the next slide, you will get anywhere from 2 to 12 comparison functions generated for you that your users can use, but that aren't actual functions in your binary. They just all get rewritten to use this. So if the user writes A less than B, it just gets rewritten to use the spaceship operator. Now, here's the advanced part of what we teach. And now we can go back to the TIE fighter spaceship if we want to. We say if you want to enable all comparisons for your class X with objects of type Y, write the spaceship operator on X that takes a Y, and then in the return type, the standard comes with several pre-built comparison category return types. They have a prefix and a suffix. If you want to support all 6 comparisons, including less than and greater than comparison, then that's an ordering. So use one of the comparison categories that ends with underscore ordering. And if you want only equal, not equal, use underscore equality. And now for the prefix, use strong by default. And that means that if 2 objects X and Y compare equal, then anything you do with them is going to have the same results. So if X equal Y means f of X and f of Y have no observable difference, use strong. Otherwise, for example, for a case-insensitive string, where that's not true, use weak. Because for a case-insensitive string, I can have 2 strings compare equal, even though they're not the same string, they might differ in case. One may have a capital letter and one a lowercase letter in the same position. And that's a weak equality because a function could do something different. Those are 2 different values, but they compare equal in terms of the default ordering. So for a case like that, you would use, say, a weak ordering, but most of the time, strong is what we want. So that's the return type. For the body, if you write equals default, you get those member-wise semantics. In the homogeneous case, when you're comparing X to X, but if you're comparing X to Y, or if you want to have something other than member-wise comparison, say you want to skip members or you want to do them in a different order, then you can just write your own function body, but you still only have to write it once and will generate all the other comparisons for the user. And here's another way of summarizing those same rules I just said. And if you just write your spaceship operator and the return type on the right-hand column, if you want to support less than style comparison, less than, or equal to, etc., make it an ordering. Otherwise, make it an equality. And if A equal B means that A and B are not observably different, so they have the same thing, you're not doing case-insensitive string comparison or something like that, then return strong, otherwise return weak. And so that's how you pick between strong ordering, weak ordering, strong equality, weak equality. And there's also a 5th comparison category in the standard that is partial ordering. It is weaker than a weak ordering, and it also permits unordered results. And you can opt into that if you're modeling something, say, like a floating point value, which also has, say, positive, negative 0, which are not ordered, or has not a number, which is not comparable to any other value at all. So think of the not a number as the canonical reason for wanting a partial ordering. So here are those same 5 comparison categories. They also have conversions, so that, for example, if you have a function that returns a strong ordering, a spaceship that returns strong ordering, that can be converted to a weak ordering, can be converted to a partial ordering. Similarly, strong equality can convert to a weak equality, and the orderings can convert to equalities. And this lets you powerfully write algorithms that actually depend on the ordering category, and perhaps they can do something different or more efficient if they're given a stronger comparison category. Now, we did not yet change the standard library to take advantage of this, but because this is already part of the machinery available for the spaceship operator, it's ready to be taken advantage of in the future. And in fact, you can go and take advantage of it in your own algorithms. Oh, one place I should say where this is already taken into consideration is we actually, after this feature went into the standard, in a totally different area of the standard, we found a use for it already in the code. So first, think of templates. You know how in templates you can have type arguments, so template type name T, that's a type argument, but you can also have non-type arguments, so you could have a template type name T, comma, int I. And so that int is a template parameter, but it's a value parameter, it's not a type parameter. Well, people for a long time have been asking, well, could I have a user-defined type in there instead of int? Could I have like my class value, and so have a value of your class. And the answer appears that we're on track to making the answer be, hopefully in C++20, that you can put a type there, a user-defined type there, as long as it has a defaulted spaceship operator. Now you might say, well, what does that have to do with the spaceship operator? Well, a defaulted spaceship operator that returns at least a strong equality. The reason is because when we stamp out templates in the language, we need to make sure that two instantiations, we have to be able to tell, are they the same or not? So if I have a template that takes an int size non-type parameter in its template angle bracket list, I know that if I pass an int value 1 and an int value 2, that those are different template instantiations. I also know that if I pass 1 and 1, those are the same template instantiation. So the problem is, how do we know what the arbitrary comparison for a particular type does? How do we know that we can compare those and get sane results? Well, it turns out that if a type has a defaulted spaceship operator because of these new rules we've just added, we know it's member-wise, and we know if it's a strong equality that we're not going to have case-insensitive style problems. And so that gives us a very nice hook that exposes the semantics of the type in what turns out to be a useful way in already another place in the standard. So that's a nice example of how exposing more information can actually help us in our code, and in this case actually helps the language do other things for us and helps us extend the language. Now, I mentioned symmetry. So now here is the rule for how you get all the two-way operations. So if the user writes, say, x less than y, so you'll notice on this slide in the top left, I'm showing x at y. Now, this at can be any of the two-way operators: equal, equal, not equal, less than equal, greater, or greater equal. What it does is it looks up x at y. So if you write x less than y, it still looks up x less than y because it may need to find your existing two-way comparison operator. But it also looks up x spaceship y, and it looks y spaceship x. What happens is that if it finds the first one, it has the same meaning as always, and these last two are ignored. And that preserves the meaning of all existing code. If you have a type that didn't have less than, though, say you try to do x less than y, but you couldn't find it, but the type has spaceship, then we say, we'll just rewrite that to, now notice we're not generating a new function, we're just going to rewrite that expression to x spaceship y less than 0. And so what is returned by the spaceship operator is a three-way comparison. You can think of it as very similar to what strcomp returns. And so it returns a negative, so compares less than 0 if the result is less. So all you do is you call spaceship and you write x at y to x spaceship y at 0. And it just turns out that putting that same two-way comparison operator and substituting it in there always gives you the right answer. So it's a very convenient rule. For symmetry, what if, for example, you did not find a spaceship that could take x and y in that order, but you found one that could take y and x in the other order? Then we rewrite it to 0 at
Herb,
y
sorry.
spaceship x, and if you just think about it mathematically.
Herb, can I interrupt you for a second? Can you please turn your video
Sure, please.
your video down? Can you please turn your video off? I think
Oh, sure.
it's camera sign, yeah, because sometimes I think the sound is flipping because of that. That's much better. And you have nice peak, by the way.
Okay. Is that much better? Excellent.
Let's try that. Yeah, okay. Thank you.
All right. And so we'll try them in this order, but then if we didn't find the x spaceship y, we'll go for y spaceship x, and then simply turn this expression backwards. So if you think about it mathematically, this is an image of the expression, and it turns out to be mathematically correct. And what this lets us do in the example with the case-insensitive string is to write, for instance, a spaceship that is a member function. The left hand is a case-insensitive string, and the right hand is const char star. And if you try to compare a string and a const char star, that's fine. You'll get this first one, X spaceship Y. But if you tried to compare const char star and string, this one will fail because there's nothing that takes a const char star and string in that order. But oh, look, we found one that takes a string and a const char star in that order, and then we can just rewrite it this way. And so this has benefits even when you're not doing heterogeneous comparison. Even when you're doing symmetric comparison, you get conversions on both sides. But when you're doing heterogeneous comparisons, like I was just saying with string and const char star, plus conversions, now you get symmetry as well. So it covers both of the reasons that you want to have symmetry. So it's actually convenient to do it in this way. And we prefer X spaceship Y over Y spaceship X is simply that if both are available, it's a tiebreak. So we prefer X spaceship Y as we just pick the convenient function. So then, when we compare a class name that has two strings, a last name and a first name, in C++17, we would have to write 6 comparison operators. And typically what we would do is we would write equality and less than, and then the others in terms of those. Notice what less than would often have to do. It would say if a.last is less than b.last, or a.last equals .last, and a.first is .first. And here, if you look carefully, you'll notice that in the case where the last are the same, that you're going to go over the common prefix that's equal twice, because maybe the last name is different, if it's the same, then we're going to be going through the common prefix where they differ in the 10th character. Well, we have to look at the first 9 characters to make sure that it's not less than. So we don't see the less than result until we get to the 10th character, and then we look at those first ones again.
Sorry for interrupting you again. I think the screen actually is frozen here. Can you move your mouse pointer?
Yes. The mouse pointer should be moving.
No, it's not. Should we try to reconnect? Let me speak
Perhaps.
to the engineers.
Let me try first just sharing the screen again.
Yeah, let's try that.
And see if that. Just one moment. Technology.
Yeah, so sorry for that.
No worries. Okay, let's try this on time. Sometimes we're just happy if it works at all. All right, so I'm just sharing again. Can you see it?
It's starting. And it's starting. And it's still loading. Let's try to reconnect. I think the Skype have some issues.
Okay, let's reconnect.
Okay, so sorry for that. Ребят, извините. Скорее всего, просто у Кербо не справляется линия. Hello?
All right. Can you hear me?
Yeah, we can.
All right, let's try sharing screens again.
Yeah. Yeah, now I can see you. Can see your screen.
Excellent. Excellent. So we were talking about how this less than comparison operator has to traverse the common prefix twice, so this is a bit less efficient than it could be. On the right-hand side, because, and this assumes that if string already has a spaceship as well, all we do is we write auto spaceship equals default. What the equals default means that we will get member-wise comparisons. And so that's what we get just by writing equals default. We don't have to write the body ourselves. And because we write strong ordering, anytime that a user will say name less than name one less than name two, we'll simply rewrite it to spaceship, name one spaceship, name two equals 0 or less than 0, whatever the comparison was. Efficient, because we're only going to take a single pass, because if you think about what it takes to do spaceship on a string, just like strcomp, you just have to go into once until you get the first non-equal character, and then you return all the information instead of throwing some of it away. You return whether it was less than, equal, or greater, so you don't have to traverse a second time because we're not throwing information away. We get symmetry, and we document by default, string is going to return a strong ordering, and so auto will deduce the same strong ordering for our class name. So what we tell people is usually, notice too that on the left-hand side, these are non-member functions, friend, bool, operator, but here it's just auto operator, it's just a member function. And that's what we tell people, usually write spaceship as a member function, because you'll still get conversions on both parameters, and you'll still get symmetry comparing, so you can put the thing you're comparing against on the left or the right-hand side. Only if you really want to enable conversions on both arguments, which I'll talk about under the pitfalls section in a moment. If you really want that, you can still write it as a friend bool, just as on the left-hand side, friend bool or friend auto operator spaceship. But generally you don't want, and then you write one function. So you still can make it a non-member friend, but generally you don't want to, you just want to make it a member. So remember, we said you need to write a cadence sensitive string and you have to write all this code. Well, now you have to write just this. Because that's less code, we can actually use a bigger font so we can see it better. What we're doing is writing two spaceship functions, one for comparing CIString to CIString, one for comparing CIString to a C-style char star string. And we document that we get a weak ordering out of it, which means we get all 6 two-way comparisons generated. So if the user writes A less than B, we just do a spaceship B less than 0, and it's just a rewrite. We're not generating a new function, it's just a rewrite. We're guaranteed it's going to be efficient and single pass, and document that it's a weak ordering. And if I write it that as the first one as a member function, I get the symmetry between comparing a CI string and something convertible to CI string and vice versa, but I don't get comparing two things that are neither, which is a CI string. If I really wanted that, I could make it a friend and a non-member friend, but usually you don't want that. Usually you don't want your comparison function to get used to compare two other unrelated types, both of which just happen to be convertible to you, unless you're doing something like writing an expression template where you're not actually doing a comparison. You're generally trying just to hook into all the operators. Usually you don't want to do that for a normal type. So since I've talked about pitfalls, let's finish by talking about some of the pitfalls. And those of you who may remember the Atari game of the same name, there are 3 pitfalls that come from anywhere from C up to C++17. The very first is actually from back in C. If you've ever seen somebody write if strcomp a comma b, unfortunately that compiles and it does not do what you almost certainly intended to do. That is a well-known pitfall, because it's going to return 0 if they're equal, which means false. That's not what most people who write if strcomp intended it to mean. And so we have coding guidelines that say, oh, never write if strcomp without comparing it to an integer, because you can see if I say if strcomp ab equal 0 or greater than 0, then I'm thinking about what the return value means. Whereas if I just allow the if strcomp, I'm probably getting the wrong result by default. Then there's a problem with if I have the two-way comparison as a member function. So here in this example, my stir operator equal const char star is a member function. And that means that if I have a stir object s, I can compare s to a const char star string, and that's okay, but I can't do the reverse because it's a member, so I don't get conversions on the this parameter, which means that the second line doesn't compile, which is not symmetric. That's probably not what I want. And so that's why we teach people, make them non-members. But then you get a different pitfall, because then if I have, in this case, an operator that takes two objects of type x, if I compare an x to a non-x that is convertible to x, that's okay. If I compare a non-x to an x, that's okay. Again, using the conversion from non-x to x. Unfortunately, it also allows this third one, which I probably mostly didn't want to allow. It allows converting two arbitrary different types. In fact, non-x and non-x can be different types from each other as well as from x. But if they're both convertible to x, suddenly the language will helpfully try to match my function if there's an implicit conversion. That's a pitfall because I almost certainly didn't want that. So now if we compare that to what we get with the spaceship operator, if we just say if a spaceship B without comparing it to 0, that's actually an error. You can't do that. We turn that off in the language, so you can't write that mistake, which the mistake that you write with strcomp. You have to compare it to something. And normally you never call the spaceship operator like that yourself unless you're implementing another one. And then you compare it against 0, greater than 0, less than 0, that kind of thing. For the member case in the middle, if I write my stir operator spaceship against const char star, I now get symmetry. So now the second version also works because spaceship rewrites equality. It tries S spaceship C-style string, and it tries C-style string spaceship S. And it will find the second one for this and make it work without giving you this problem. So that, again, if I make it a member, which is what I want to do most of the time, I get the symmetry of conversions, but this correctly, it's green because it doesn't compile, which is what we want. It's an error, so I do not implicitly get it on unrelated types. Now, if you really wanted that, that's okay. You can still do that. Just write it as a friend. But by default, just write it as a member unless you really want that behavior. And so we save a lot of pitfalls on the right-hand side. So that's a summary of what's new in C++20. Compilers are starting to implement it, so I expect the first implementations of this to be available later this year. And so that's a new feature that's one of the early ones in C++20 that you'll be able to use in your code soon, or as soon as you're able to upgrade your compiler for the new feature. And happy to take any questions that you may have on that or on other C++ topics.
Thank you very much for your talk. So guys, if you have a question, please raise your hand. No.
Are there any plans to introduce something like this for other operators, like enforcing symmetry for plus, minus, or maybe other algebraic properties?
It has been suggested.
I think we have troubles with the sound. Can you please
on
repeat?
the table to do those things.
Can
Yeah,
you please
it's been
repeat?
suggested, but there are no proposals yet to do that.
Thanks.
Yes. Can you hear me?
Yeah, we heard
Okay.
when you repeated. Any other questions, guys? Okay.
A very small question. Does it mean that as soon as you write this spaceship operator for your custom user type, then you can no longer overload normal comparison operator?
Excellent question. Yes, you can. So if we go back to the rules I was showing, let's go back here. Finding the right slide. There we are. You'll notice that we look up in order the two-way operator, and if we find that, we use it. Otherwise, we use spaceship. Most of the time, you will only want to write spaceship, only need to write spaceship. However, there's a very good example of where you can do better. So consider vector comparison. If I compare vector equality, I can very quickly, without looking at any of the elements, find out the two vectors are not equal if they have different lengths, for example. So for vector, what we will likely do in the standard, as this gets adopted into the standard, is that vector will get a spaceship operator, and certainly if we were doing vector from scratch, it would get a spaceship operator, but it would still get equal, and not equal two-way operators because they can be more efficient. If all you want to know is equal or not equal, we can often short circuit that just by looking at, are the lengths different? And then without even looking at any elements, say, oh, they're not equal if the lengths are different. So that's an example of where you might use it. Otherwise, unless you can write them, so if you have a more efficient implementation, you can still write the two-way operator yourself. Much of the time, spaceship is going to be optimally efficient because you're going to have to scan the contents anyway. And in those cases, spaceship will be able to do that more efficiently because it'll be able to do it one pass. But you can still overload a two-way operator if that makes sense for you.
Thank you. Any other questions, guys? John? Okay, Herb, can you please explain that, is there likely that this operator will make it to the new standard, to C++20?
It is already adopted in C++20.
Oh, okay, thanks. I missed that. And is this true that we get rid of the row pointers? Sorry, I ask everyone about that. So, guys, do you have any questions? Okay, thank you, Herb. It was really interesting and
Yes.
a new experience with the Skype. Sorry, it's falling apart again. We can't hear you. Okay.
All right.
Okay, thank you very much. It was really interesting, and I think we're gonna shut it down now. Right? Okay, guys, thank you.
All right. Thank you. Have a good evening.